Okay, we have here another integral on the board. I've got the integral from 0 to 2 pi cosine of the fourth x dx. Okay, so recently I did a really similar problem. We did cosine cubed x. Now the reason I'm doing this is because now with the fourth power, this is actually an even exponent. The other one was an odd exponent, and that's going to make a pretty big difference on this. So again, what I'm doing here, I'm not going to use the optimal method. I'm going to use the complex definition for cosine of x. We'll look at this as e to the ix plus e to the minus ix over 2. And now that we have this, I want to just find cosine to the fourth x. And for this here, you can just kind of multiply it all the way out, or you can use Pascal's triangle or binomial coefficients. So just expanding this all the way out, I'm going to take the 1/2 out, take it to the fourth power. That gives us 1 over 16. Then for this first term, we're going to have just e to the 4ix. For the second one, the coefficient is going to be 4. We end up with e 3ix times e minus ix. Then we're going to have a 6. E 2ix, e minus 2ix. Then we'll have another 4 here. This becomes e minus 3ix. And this last term is going to be just e minus 4ix. But we can get some simplification here, so this is going to stay the same. But here, combining this and this is going to become 4 times e 2ix, just combining the exponents. Now here, when you multiply e 2ix times e minus 2ix, you get e to the 0. That's just 1. So we're just going to have a 6 here. This one's going to be e minus 2ix, and this one's going to be e minus 4ix. So with this here being our cosine of the 4x, we can just take all this and put it back in our integral and continue. Okay, now at this point we can actually just integrate this and finish it off. It's not too bad. But my thinking is, what if the exponent was bigger? What if it was to the 20th power? What if it was to the 100th power? Then we wouldn't want to integrate 100 terms. So what I want to do instead is just kind of look at like one term and kind of make it generic. So instead of looking at 4e to the 2ix, let's still integrate from 0 to 2 pi, but I'm going to say we're integrating a to the e bix. Now when we integrate this thing, we're just going to end up with a over bi, and then we're still going to have our e bix evaluated. And we're going to evaluate this from 0 to 2 pi. So then plugging in, we'll have this out front. Then we're going to plug in our 2 pi's. This is going to give us e to the 2 pi bi, and then minus, we plug a 0 in, e to the 0 just becomes 1. So now to figure out what's happening, we just need to evaluate this piece right here, and for that, we'll just use Euler's formula. Okay, so we have Euler's formula over here that's going to let us put this in terms of sines and cosines. Now for this x value, you notice we have the I, but our x value that we're plugging in here is going to be 2 pi b. So just bringing this thing down here. So for our x value, this is just going to be 2 pi times b plus I sine 2 pi b. But now the important requirement on this is that b needs to be an integer. If b is some fraction, then all bets are off. But if b is an integer, then here we have some integer multiple of 2 pi. Sine of a multiple of 2 pi, this is going to 0. And then cosine of 2 pi b, again with b being an integer, any integer multiple of 2 pi, this is always going to be 1. So this thing is always going to be 1. This is 1. But 1 minus 1 means that this expression here is always going to be 0. So what this is going to allow us to do is cancel this, because this is 0, this is 0, this is 0, this is 0. But this isn't 0, but this is 6. But what we can do is clean everything up and just deal with 6. So the key takeaway is when we have an even exponent, everything's not going to cancel out. We're going to be left with some constant term. But now this is going to be easy to deal with, so we integrate, we get, this is just going to be 6x over 16. And we need to evaluate again from 0 to 2 pi. Well, the 0 is just going to be 0, so I just need to plug in 2 pi here. We end up with 12 pi over 16. But if I just reduce that, we get our solution of just 3 pi over 4. Okay, good problem. We'll stop it there. Thanks everyone for watching. Have a great day.